A sheep farm in northeast England, where the farmer is making sure the grass is in top condition. A fertilizer containing nitrogen is spread over the fields during the spring and summer. Nitrogen trebles the rate at which the grass grows, so there's plenty of grass for food for the animals. The nitrogen in the fertilizer is in the form of nitrate. Nitrate does occur naturally, but most nitrate is manufactured. 2 miles away from the farm is Teesside, and one of the largest chemical complexes in Europe. Here, nitrate is made by a process which was invented at the time of the First World War.
People were concerned that we didn't have enough nitrate to keep feeding the world. Nitrate's good as a fertilizer, and the population was growing so quickly, scientists were worried that we would use up the world's supply of nitrate.
The first stage in nitrate manufacture is the making of nitric oxide gas. This is made from 2 other gases, ammonia and oxygen. The gases pass along large pipes into metal reactors. But ammonia and oxygen don't react together easily, so inside the reactor is something which helps them react to form nitric oxide.
Well, for the first stage, the important thing is the catalyst. Without the catalyst being present, we'd only get approximately half of the yield of nitric oxide that we get when the catalyst is there.
The catalyst is a substance inside the reactor. It speeds up the reaction between ammonia and oxygen. Sue can't see the catalyst, only the heat given out as the gases react. But another reactor is being prepared for the addition of a new catalyst. Using a crane, the reactor top is lifted off. And this is the catalyst which will go into the reactor. 10 sheets of very fine gauze. It's not fabric, but woven strands of the precious metals, platinum and rhodium. The gauzes are very expensive. In fact, they cost hundreds of thousands of pounds. But it's money well spent, because once inside the reactor, the gauzes catalyze, greatly speed up, the reaction of oxygen with ammonia. After the lid is replaced, the gases will pass into the reactor and come in contact with the gauzes, where nitric oxide is formed quickly and without adding a lot of heat. So how important are catalysts to the chemical industry?
For a lot of reactions which we wish to do, the rate of reaction at normal conditions is so slow that it wouldn't be economical to build a plant. So catalysts make the rate of reaction quicker at normal conditions, so that we might be able to construct a plant economically to make the product which we require.
But how does a catalyst work? At the University of Manchester, catalyst expert John Salthouse explained with a simple example.
We're going to look at the reaction of the decomposition of hydrogen peroxide into water and oxygen gas. Hydrogen peroxide solution is remarkably stable. If we pour some into a test tube, little oxygen gas will be evolved. We can heat up the test tube and bring the solution almost to boiling, and still little oxygen gas is being given off. We can test for the presence of oxygen gas by its ability to relight a glowing splint. And as you can see, no oxygen gas is being given off, the splint is not rekindled. The catalyst that we're going to look at is manganese dioxide. It's a black powder. The moment the manganese dioxide meets the hydrogen peroxide solution, effervescence takes place, oxygen gas is given off, and in fact the mixture gets quite warm. And we can test for the presence of oxygen gas by its ability to rekindle the glowing splint.
Is any of the catalyst used up?
The powder isn't used up, and it presents a very large surface area for the reactions to take place. We can filter off the powder at the end of the experiment, and it is just the same as the manganese dioxide that we put in the first place.
So if the catalyst isn't used up, how does it work?
On the surface of the manganese dioxide, there are what are called active sites. Molecules become absorbed onto these active sites, the reaction then takes place, and the products are released.
Why are catalysts so important?
Catalysts are used extensively, particularly in chemical industry, to enable reactions to take place with the minimum expenditure of energy.
Chemicals are made up of molecules which move about randomly. Molecules of different substances don't bump into each other very often, so sometimes reactions can be slow. But when a catalyst is added, it seems that molecules gather on the catalyst's surface at special active sites. Taking a closer look, molecules of different substances can be brought close together at these active sites. The catalyst apparently helps the molecules to react to form a new substance. So catalysts speed up reactions. But catalysts aren't found only in industry, they exist in the natural world. Turning milk into cheese traditionally uses a catalyst found in animal stomachs. Catalysts found in living things are called enzymes, and the enzyme which changes milk into cheese is called renin. Renin solution is added to sour milk and left to act. After only 15 minutes, a solid top forms on the milk entirely because of the action of the renin. This is the start of making cheese. The enzyme always acts in the same way and doesn't need a lot of heat to work. When the liquid is drained out of the vat, solid lumps remain. These are salted and dried to make cheese. Enzymes in our bodies catalyze the breakdown of the foods we eat. But there are special enzymes which work on starches, other enzymes on proteins, and yet more enzymes on fats. We perform well because every enzyme has a particular job. Using enzymes, our bodies work efficiently. But how do enzymes work? We think it's to do with shape. A molecule and its particular enzyme. The molecule fits exactly into the shape of the enzyme like a key into a lock. The enzyme then helps the molecule to break down. But only molecules of the right shape fit into that enzyme. That's why enzymes are called specific, which means that they only act on one type of molecule. In industry, scientists have now started using enzymes as catalysts. When did this come about?
I think this has only come about in recent years because biological science has progressed a lot in the last few decades. We've come to understand that enzymes are just biological catalysts and can perform a lot of interesting reactions.
Here, a particular enzyme is being made which will catalyze the making of fructose, a very sweet sugar, from starchy foods such as potatoes. Using the enzyme will provide sugar in countries which can't grow their own sugar cane or sugar beet. But what's the advantage of using an enzyme?
The principal advantage is the enzyme specificity. That's to say, it will only cope, it will only change one molecule out of many that are presented to it. one type of molecule. So that if you give an enzyme a mixed stream of chemicals, it will just pick one out and change that into something you want, and all the rest will pass straight through.
The key and lock action of enzymes is important. Natural substances like sugars are very similar, but the specific action of an enzyme ensures that only one sugar, fructose, is made. No unwanted sugars are produced.
But there's a second aspect to that, which is the mild conditions under which enzymes work in terms of temperature, pressure, and pH.
This is dried enzyme. It doesn't need a lot of heat to work. An important point is energy is very expensive. So enzymes are specific and work at ordinary temperatures. Do chemists like Stephen think they'll take over from traditional catalysts?
No, I don't. My belief is that the bulk chemical processes will stay with the traditional inorganic catalysts. I don't think they've run out of developments yet either. But I do think there'll be lots more uses for enzymes in the coming years in those areas where their particular properties can be used to advantage.
Catalysts, either chemical or biological, are found throughout industry, making reactions fast and easy. But recently, catalysts have been used in rather different places. Los Angeles, California, where the car reigns supreme. There are more cars per person here than anywhere else in the world. But all those vehicles produce over half the air pollution in the city. Los Angeles is in a valley, so the pollution can't easily escape. It hangs over the city as smog. Attempts to get rid of the smog led to the development of pollution controls on cars.
Well, there was an evolution of controls. They started out being rather simple devices. We were really pioneering in this field, especially here in California. But each year the standards became tougher, the rules, the smog limits became tougher. So we developed better and better systems. But in 1975 we began using the catalyst. And the catalyst has proven to be a major control for automobiles. It's done a very effective job in cutting down all of the major pollutants by acting on the exhaust gases chemically.
The catalyst is a precious metal device fitted in all Californian car exhausts. But it's a British firm which is a leader in catalyst manufacture. Just how important is their catalyst?
It reduces the pollution coming from the tailpipes of automobiles and makes our towns and cities healthier places to live. The catalyst is a honeycomb material coated with a precious metal such as platinum. We are sent the honeycomb cylinders. We put them on the production line and coat them with a liquid material which gives the honeycomb a much higher surface area, equivalent to 3 or 4 football fields.
The honeycomb is then coated with platinum metal, which is the catalyst. The catalyst becomes spread through all the channels, so it has a very large surface area on which the exhaust gases can react. The catalyst is fitted into a can and put into the exhaust. But how does the catalyst work?
The harmful pollutants coming from the engine, which contain carbon monoxide, unburnt hydrocarbon from the fuel, and nitrogen oxides, pass through the catalyst and they are converted to harmless components, carbon dioxide, water, and nitrogen.
And the huge surface area of the catalyst means there are very many active sites where the harmful gases can change into harmless ones. So catalysts in the exhausts of American cars help to reduce air pollution. But regular checks are needed to see that the catalysts are in good working order.
We do have a program for testing on-the-road vehicles. We require that they have a smog test when they change ownership.
At centres like this, the pollution control devices on cars have to be tested before the car can be registered to go on the road.
initially, as the car approaches the test center, they have to punch up the car on a computer. And this tells them what standards that the car has to meet and what systems should be on the vehicle, smog control devices. The car is moved up to the dynamometer area and placed on the dynamometer, which is a device that has rollers for the back wheels. We insert sensors or sniffers up the exhaust pipes, and this takes a reading, measures the amount of pollution coming out of the car. Then when the engine is started, the car is put through a driving cycle of speeding up and slowing down and cruising at 40 miles per hour. It simulates the conditions that you would encounter if you were driving in a metropolitan area. And while this is going on, well, that sensor is measuring that pollution, and it's being recorded on our instrumentation, so many grams per mile of the various pollutants.
If a car passes, a test certificate is issued. But even a 2-year-old car may not meet the strict test requirements.
Okay. No, the car did not pass the test.
So the catalyst and other smog control devices have to be brought up to standard at special repair garages. But has there been a real reduction in smog since catalysts have been introduced?
Well, we have a very difficult situation here. There has been a downward trend in pollution. I would say very definitely if we didn't have these controls on automobiles and industry, that you wouldn't be able to see across the street at certain times of the year when you have bad smog conditions, which are about 5 months out of the year.
But in Britain, our cars are still giving out poisonous gases. Why aren't we using catalysts?
To be introduced into Britain, the first thing that should happen is that lead is taken out of the gasoline. Precious metal catalysts are poisoned by lead, which is in normal gasoline in this country. In other words, they cease to work. So therefore, it is not possible to use them on vehicles in this country at present.
Normally, the exhaust gases collect at the active sites on the catalyst and are converted into harmless substances. But if a poison such as lead is added, it blocks the active sites, so the toxic gas molecules can't reach them and can't be turned into non-toxic chemicals. The harmful exhaust gases pass over the catalyst unchanged because the catalyst has been poisoned. Petrol in Britain contains lead, so catalysts can't work. A change to lead-free petrol would mean that cars could be fitted with catalysts and pollution by exhaust gases would be reduced. Using lead-free petrol would also mean that levels of lead in the atmosphere would go down. The air would be cleaner, and our cities would be healthier places in which to live.